So, what is this problem? We have already seen it, no? So, what are the things that are given and what is to be found? Decision version. There are certain objects, right? Collection of, say, things, and there is certain weight for each of them, and there is also a profit associated with each of them, right? And you have a budget B. Okay, let me call it B. Okay. Say given, say, n items, say A1, A2 to AN, okay, and let me say it is a profit of taking each element. It's a function from A to, what is it? It can be any real value, or how was it given? The profit was actually given as integers, okay, positive integers, okay. Okay. Now, for each item there is also a weight, right? It's also positive, integer weight, okay. So, I am writing the optimization version now, okay, not the decision version. So, find, okay, also given a budget B, which is the maximum capacity of the bin that you can take. The total weight of the items taken should be at most B, the sack, that is the sack capacity, right. So, question, find a collection of items from A such that their, what is the constraint? Total weight is less than or equal to B, that is the constraint, and what do you want to maximize? Total profit. Okay. So, in the decision version you are also given a profit, target profit, and the question is, can you get at least this much profit, right? And here the question is, what is the maximum profit that you can achieve? Okay. So, this problem, what's the, if we think about the size of a problem instance, right, that is the parameter with which we are trying to, as a function of the input size, we always try to bound the running time, right. So, what is like the, if there are n items, what is the input size here? The input size typically what it is, when we try to represent it in a computer, as say we are giving it as input, what is the size, okay. this is n different items, that is okay, you can even think of it as 1 to n, okay, n different things are there. So, the size is at least n, okay. Now, this profit and weights, they are numbers, big numbers, right, correct. So, maybe you have a 10 digit number. So, what is the size of this number? Say I have say 10 to the power 10 as a number, or say I am writing this number 12586. What's if this is one of the weight of item 1 and or say profit of item 1 and weight of item 1 is say 12, such numbers can come, right. So, this is also part of the input. So, are they affecting the input size? If you have big numbers, it is, right, you need space to represent them, but still this is a how much space do you need to store this number in computer? Does it need as much space as proportional to the magnitude of the number, or is it like it is proportional to the log of the number only, right, that is the number of digits. The number of digits, if it is digits, it is like log to the base 10, right, 5 digits, and if it is log to the base 2 in computer, then it is this number to the base 2, right. So, to represent a number of magnitude n in computer, we need log n bits only, right. So, so you can say that if the maximum profit here is say capital P, right, so if capital P is the maximum profit, and capital W is the maximum weight, then n into log P, okay. This is the n into log P and n into log W. These two things are required, this may be required, this much space may be required to represent the weights, all the weights together and all the profits together, right. This is the worst case possible. Plus you have that 1 to n numbers, so let us say n, slightly more than n, okay, but whatever this. So, the input size here is like n log P or n log W, I mean plus the addition of all these things, okay, and it is, okay, keep this in mind. So, our algorithms, if we are obtaining a polynomial time algorithm for this problem, it means that it can have running times like n log P, n square log P kind of things. Whereas, if you get some algorithm in which the running time is like np, okay, it is not polynomial in input size. Because our input size is not really polynomial in P, but it is exponential in P. I mean, it is logarithmic in P, right, the input size. So, as far as the input size is concerned, if you have a P term, it will become an exponential algorithm, right. Are you following? Say, if you have studied this max flow min-cut problem, the first algorithm that you study is Ford-Fulkerson algorithm, probably. I do not know how many of you know, but you might, if you have not studied, if you are in computer science, you will study it in future, okay. So, that algorithm is very easy to explain, but in the worst case, so that in that problem also you have certain edge weights given in a graph. So, the running time of that algorithm is a function of the maximum weight that you see on the edges. It is not a function of log. So, there also the problem instance size is actually like log of the maximum weight. So, and the Ford-Fulkerson algorithm in the worst case can take something which is like W into something, W into n cube or something. Okay. So, that algorithm is another algorithm which is like it is not polynomial in input size, but it is polynomial if you think that these numbers are represented in unary, right. If you just represent these numbers, all the input using unary, that is, if for representing one number you are writing that many ones, that is your input representation. That is a very bad representation, nobody will use it. But if that is the case, in that parameter this algorithm is polynomial, these type of algorithms. If it is taking running time NP or NW, these kind of things, N square W, all these things, they are called pseudo polynomial time algorithms. They are not really polynomial time algorithms, because in terms of input size they are not polynomial. Okay. So, these are all representing pseudo polynomials, whereas this is like it is a real polynomial in input size, because log p is the term which we have in the input size, not p. Okay. Okay. This is just as a background for this problem. So, now suppose you know how to solve the decision problem is of this thing in polynomial. You do not know, but just for a moment assume that you know how to solve the decision problem. Then in polynomial time, say it is not possible, but assume it is possible. Then can you derive a polynomial time algorithm for the optimization version? So, the question is, should be polynomial, okay, real polynomial. That means it should not have this p coming in or anything like that. Okay. So, the decision version will have a profit also given, target profit. Can you get profit at least this much in addition to this, instead of this maximum profit, it is can you get at least p profit. Okay. So, the question is, suppose you know to solve the decision problem in polynomial time. Okay. Knapsack decision problem. Then can you find a polynomial time algorithm for the optimization version? So, if it was vertex cover problem, I had the answer for decision problem. Then how will you tell me the corresponding, if you know how to solve decision problem, how will you solve the optimization problem? Run it for all values of k, right, from 1 to n. Then whichever gives you the minimum value for which the decision problem says yes, take that, right. That was how you will get the optimization version of vertex cover using the decision version. So, will the same strategy work here? Why or why not? Similar strategy. If you run the, what is the maximum profit possible? Maximum, can you give me an upper bound for the maximum profit? all the elements together, sum of all the profits, right? That is the upper bound.
And you have a least also. You have a least also.
You have a least also.
Then by binary search, I guess you can.
So that is an idea. So why do you need binary search?
Because it will take log p time.
Correct.
That's
So okay. So if you start checking this for all the possible profits one by one, so the minimum profit may be like it's a 1. Okay, 1 is a lower bound, or a better lower bound is minimum of all the profits, right? Okay, so this is a lower bound. Or I cannot say this because okay, let us assume that we do not have any elements whose individual weight is above the bin capacity. Such items anyway we cannot take, right? Such items we will eliminate in the beginning itself. Okay, we will have that assumption. Okay. With that assumption, this is a lower bound. At least one item you can take. So this is a lower bound. Otherwise, it will be 0. Okay. And an upper bound is sigma pi, right? So there are many values in this range, right? Anyway, this is greater than or equal to the maximum profit, right? P max. You cannot simply go on searching for every possible profit from say 0 to P max, because that will take P max many rounds, right? That is not really a polynomial time algorithm, right? That many rounds you cannot repeat. So what he told is a nice one. So you do not really do that. Instead you can do some binary search, okay? So you initially search if you can get, you take this maximum, let it be some P sum or something, check if that is possible. If that is not possible, check if it is half P max by P sum by 2 is possible. If P sum by 2 is achievable, by the decision problem will tell you if it is possible or not. If the answer is yes, you can search the midpoint of this range. If it is not possible, search the midpoint of the lower range, right? In this way, in log P rounds, by log P invocations, log P to the base 2 invocations to the decision problem, you can solve the optimization problem. So that is okay. The obvious thing that we would do for a vertex cover, you cannot do here. Okay. So by so the answer to this is yes. Now, if you know the decision optimization problem's answer, you know how to solve decision problem, right? That is very straightforward. Just compare whether the profit given is more than the optimum or less than the optimum, right? If you know the optimization problem's answer, for a particular value of profit, target profit, if you ask the question, it is very easy. One invocation is sufficient, right? So, that direction is trivial. Okay. So, given that, now let us think of some way to solve this problem. Okay. So, first what we will, okay, you know that this problem is NP complete, right, the decision problem. Yes. So, actually for this problem, yesterday we saw the TSP problem where we told that no approximation is possible, right, but this problem is on the other extreme. It can be approximated as close to one factor as you want. You cannot get one factor because that is a contradiction, but for any epsilon, this is a maximization problem. So, your factor is less than 1, right. You can reach, if you want to reach 0.99 factor approximation, you can reach that. If you want to reach 0.999% factor approximation, you can reach that. So, whatever epsilon you give me, I can go that close, 1 minus that epsilon close. Okay. So, this problem is like that, very well approximable problem. So, first let us try to get a 2 factor, which is very easy. Okay. Then we will get the better solution, half factor, not 2 factor, half factor approximation for this problem. So, before that, can you write the LP formulation, ILP, integer linear programming formulation of this problem? From that we can derive we will get some argument that can be used to get a 2 factor approximation, ILP formulation for this. So, here unstated assumption is that you cannot fraction any item and take it in part, you have to take it in full, right. The what is this? C1?
C1 costs, each assigned costs for an I item. C1 is the cost and X1 is whether it has been chosen or not, 0 or 1.
Cost or profit?
Sorry, profit. This is the profit.
Okay. You need variables.
Multiple profit and weight plus.
Why multiply with weight? Profit is the total profit.
No, individual part, things, product, things T1 to T10, some items.
Correct, but how can you?
Item number and that is around weight.
No, this is not per kilo weight profit. This is the total profit. I am telling you, I have say 1 gram of gold. Its profit is 10,000 rupees. I have a big iron rod. Its profit is so much. You cannot break it. I don't say 1 kilo of iron is this much costly. I am telling you this is the cost of the total item, profit of the total item. If you take it, you take it. If you don't take it, you don't take it. What is A1, AN?
At elements. Elements I'm fixing whether it is 0 or 1.
Hmm?
A, it will be 0 or 1 for all.
If you write like this, it's not 0 or 1. It can be any value between 0 and 1. It belongs to 0, 1 set is what you would want to write, right? Hmm? Okay. What is xi?
Items.
You cannot add items, no? Number of items is n. What does the variable xi represent?
Sigma.
No, that is not the thing. What you wrote was okay, but you have to tell me what is xi. What does xi represent? So, in vertex cover, what was xi? Whether that vertex is taken into the vertex cover. Here, similarly, you have to give me an interpretation of the variable, whether the item is taken or not. So, write it that way. What is A1, A2 to AN?
Number of items.
Number of items. Number of items is n.
I choose this variable. I choose this variable.
No, n is given in the problem that n is the number of items. You cannot change
The
that.
quantity of item 1.
Quantity is 1 or 0. Say you either take it or not take it. It's not like you take half of it. You cannot do that. See, this profit is given for the entire item. You cannot break it. It's not like per kilo profit. It is for this big item.
I mean, I can't take 2 items of.
You can take 2 items. No, you don't have multiple numbers.
Okay, either take it or leave it.
If you have say 2 things which are similar, you consider it as 2 items A1 and A2 separately. You don't have two things identical to take and you make it number. There is no number. Every item is 1. Write it. So, what is this variable xi?
If I'm taking A, it is 1.
Okay. So, what is the constraint now? Alpha, let's use B. B is our thing, right? Okay.
But we have to put it for each constraint for each.
No, this is the only constraint, right? This is correct. Okay. So, most of you have got it. So, the ILP formulation is very simple. It is that let xi denote whether item AI is taken in the solution or not. So, xi is 0 or 1 depending on that. Okay? 0 if it is not taken, 1 if it is taken. So, you have to maximize the sum of the profits of the items taken, right. So, it is sum Pi, let me call it Pi instead of profit I will call Pi, Pi xi, I is equal to 1 to n, subject to, people are not convinced that it can have just one constraint. Some people are thinking there should be many constraints for each something. Okay, there is only one constraint here, that is that the total weight of all the items taken should be at most W, right. So, sum of I is equal to 1 to n, wi xi should be less than or equal to the budget. Okay. So, this is the ILP formulation. So, if we find the opt ILP value, that is our actual answer. Now, suppose I do the relaxation now. What does that mean? Physically mean if I allow relaxation. So, that means I can take fractions, right? Fractions, any item, if I want to take half, if I want to take 1/10, I can do whatever fraction I want to take of each item, I can take, right? So, I may get better profit, right? This is a maximization problem. So, LP relaxation, xi can take any value between 0 and 1, right? Right? So, since this is a, so this physically mean can take items in part. So, since this is a maximization problem, what is the relation between opt ILP and opt LP? For any instance, yes, right. If we allow fractional items, you may get more. Any integral solution is a fractional solution also. So, this is the relation, right, for any instance. So, now do you have a polynomial time method? I mean, it's a very easy thing. How can we, if we allow fractional things, if you can break things and take it, how will you maximize the profit? What is the strategy that you will use? If you are allowed to take items in part also, what should the thief do so that he can get the maximum profit? 1 by? So, we should think which is the most profitable item, in the sense that per weight what is the best. If you have gold and you have iron, then even if it is 1 gram of iron, or you will say what is the benefit. If I take 1 gram of iron and 1 gram of, you will compare, no? Weight per, price per weight, profit per weight. So, the maximum one is the better, right? So, you can arrange the items in the order of their price per, profit per weight, and then what is the strategy? To get an optimal fractional solution, arrange items in the decreasing order of, non-increasing order of Pi by Wi, right? So, let us rearrange the items now. Find Pi by Wi for all items and just arrange the items such that they are in increasing order. So, from now on, say without loss of generality, let us assume that P1 by W1 is greater than or equal to P2 by W2, etc. Okay. So, you have arranged the items such that the maximum precious thing is arranged first. Now, what will you do? How will you take it?
We can take the whole part if it is our capacity is given.
Right? You will start picking the first item as much as you can, right? If it does not fill the capacity, then you take the first item in full and take as much as possible from the second, right? So, you will stop at a point where all the previous items could be taken and this item maybe you will take it in part, right? That is the best, no? If you have anything else, your profit can be made better. If you were choosing something else as your solution, then I can certainly increase the profit by throwing away some iron, say 1 gram of iron I will throw away and instead I will take 1 gram of gold, right. I can take a more precious thing of the same weight if that was not my solution. Okay. You gave me one strategy which is greedy strategy, right. I am telling you that is the optimum possible also, because if at all there was some other solution in which I was, instead of taking some item in full, I had taken a less precious item in some part of a less precious item and I had no place to put this bigger, more precious item. Why do I do that? I just throw away the same weight of that less precious item and take an equivalent weight of the more precious item. I am only going to increase my profit, right. So, greedy will always give us an optimum solution for if we are allowed fractional to take items in part. Okay. So, it is not difficult to see that greedy strategy will give the optimum fractional solution. So, what we just told is, we know how to find, even without running that LP and all, we know how to find this one, opt LP. We know how it looks like also, right. This is the greedy algorithm. Okay. We know how it will look like. So, let us see how a solution will look like for the fractional solution. Okay. So, now I am assuming that my elements are arranged in this order, okay, in the sorted order of profit by weight. So, how will an optimum solution, an optimum LP solution look like? Okay. Optimum LP solution. What should I give? How much of each? What is the value of each xi? Each xi can take values between 0 and 1, fractional values, right. So, it will be something like, I have taken some initial items in full. So, x1 is full, x2 is full, etc. And so, maybe this is the some kth item. Till there I could take everything in full. Maybe k is 0. Okay. And the next item I could take only in part. Right. So, this is some alpha how much of it I am taking, okay. Is it full or is it half of the item, okay, this is, and remaining items I am not taking at all, right. So, this is my, this is how my optimum fractional solution will look like, not the value, but this is how the values, the x size will be, right, and alpha is right, alpha could be even 0, alpha cannot be 1, then the next, that also I will say it is k, okay. Till where it is full, that is where I am calling it as xk, right. This is how a optimum solution, any optimum solution will look like this, okay. So, now let us look at two other solutions. Okay, one assumption that I stated but did not write down, assumption weight of any item, any one item is less than or equal to b. Otherwise, you just discard it initially itself, you do not need to consider it, right, you can never take it. So, that is one assumption. So, I can have two other solutions. One solution is just up to xk I take, okay, and it is all 0 here. What does this represent? I do not take the k plus 1 item at all, but I take all the first k items. That is, if greedy could have taken some items in full, that items I will take. So, this is an integer solution, right. This is a solution for ILP, right. So, let us call this as solution 1, and another solution is I do not take any of these items, but I take this item in full. Is this a valid solution? Is this, I take valid solution, I am not asking you whether it is an optimum solution or something, I am asking is it a valid solution. Any item I can take because it is singly, if I take it, its weight is less than b, less than or equal to b, right. So, this is also a valid solution. We will initially discard it and we will assume that in our instance there are no such items, because we cannot anyway take it, right. Just discard it. So, without loss of generality we can assume this. So, these are two valid solutions, right. Both are integer solutions. So, what does it physically represent? The first solution represents if greedy was to take k items in full and k plus 1 item in part, take only the first k items. So, that is solution 1. Solution 2 is take the k plus 1 item. So, the claim is that you compare the profits obtained by both these solutions, they are both integer solutions. The best of them will get at least the maximum, the half of the maximum possible. So, my claim is you choose the best among these two, it will give you at least the maximum possible profit divided by 2. So, how can we show that? So, what is the profit of this solution? Profit. So, claim is, okay, so let us write P of S1, profit of S1 is the sum of profits, right? It is P1 to Pk, right? And P of S2 is Pk plus 1. So, my claim is that maximum of these two. So, this is my claim. It is at least half the optimum value possible. So, can you try to prove it? So, this is not a ILP solution, but what is its profit? That is opt LP, right? What is it? Opt LP. P1 plus P2 plus Pk plus alpha Pk plus 1, right? So, this is my opt LP. Opt ILP is less than or equal to this. So, now do you see the proof? Just think of it. Alpha is between 0 and 1. It is less than 1. Alpha is less than 1. S2 is a solution because any individual item, I have the assumption that its weight is less than or equal to B. So, that item alone you can take always. It is feasible. It will fit.
But it will not be
Optimum.
It will not be optimum. I am only saying it is a feasible solution. It is a valid solution. I am not saying it is optimum. I never told that
but
any of this is optimum.
So, but profit of S1 will be always maximum in that case.
No, we do not know.
Are
Because
those?
we are arranging it in the profit per weight order.
Mm.
So,
Then isn't it obvious that S1 will be maximum?
It is not obvious. Actually, we can have some examples. We will do it as an exercise now. That there are cases where that will be very far from being optimum. Forget about being optimum. It will be very bad compared to the optimum. If you only assume that you can take S1. Okay.
We are choosing those items by taking that ratio.
Correct. So, okay. So, now since many people are asking this question, the question is, why am I taking the maximum of these two? Why can't I just take S1 as the solution? Okay. Now, your exercise is to find one instance of this problem where by taking the greedy strategy. So, your strategy is this: arrange items by profit by weight, take it, you cannot take anything in fraction. So, the moment that you cannot put in the next item, stop, right. That is the strategy. So, give me an example of an instance. Instance means you have to give me weights and profits of items such that this will not give you an optimum solution in the integral case.
Why are we approaching this by the subset sum problem? No, sorry, the minimum cost vertex cover problem.
I am not.
Why aren't we doing by that? But why aren't we using that approach?
Why are we?
Like over there, it was a similar problem for the minimum cost vertex cover problem.
Huh.
Over there, we did this approach that for 0.5 we approximated to 1.
Ah.
And
I am not doing that here.
why aren't we using that?
For each problem, if you can show the guarantee, then you can use it. If you cannot show, then you cannot use it.
Like if the argument that we used over the exact same argument we can apply.
What is exact same argument?
Like for that less than equals to twice of that, how did we show that all the costs are positive, all the coefficients are positive, and we are just taking the 2 times is always would be point, like for any number greater than 0.5, the twice of that would be greater than 1. So by that it is two factor.
No, 2 factor, because we increased any 0.5 only to 1.
Yeah.
The increase in any variable was by 1 only. I mean 2 factor only. That's why, right? We got 2 factor. And we also know that ILP and LP are related like this. See, the thing is, certain approaches, when you see, that is why we are learning this, right? If each problem is different, why should we learn it? If you are intelligent, you will find it, right? We are learning it because there are several patterns in several problems which look similar, right? And with practice, it will come to you that, okay, this strategy may be similar to that strategy. Can I have something like that? Otherwise, we don't learn anything, right?
Like is it some like this is better for using that? This strategy is better. That's why we are using it.
See, I see that you will try to use several strategies. If you can get a guarantee, it's good. If you cannot get, then you will have to look for other strategies. So can you give me some where taking the other items may be better? You leave out 2-3 items are enough, I think. Don't think of many items and all. With 2-3 items, you will be able to get it. Okay. So this weight can be very big. Say W2 can be 1000 or 10,000. W1 can be something very small, say like 1. Okay. Okay. So just this instance is sufficient to show you. So there are two items. The first item has, you have only 1 kilo. Okay. It is very precious. It is 100 rupees per kilo. Okay. You can have any higher number also, but you have only one. Right. Here you have another item which is cheap, but you have a large quantity. Okay. But your bin capacity, you cannot take both. Bin capacity is exactly this, 10,000. What will you do? If you take that smaller precious item, then you will get total profit of only 100. Right. If you take the second item, it is not that precious, but because it is 10,000, you can put the entire thing into the bin, you can get 10,000. So there is a factor 100 difference, right? I can make this as big as I want. I can put one more zero here and bin capacity also. So the factor by which I am away from my optimum solution. Here you know the optimum solution. Take the second one, that's the optimum solution. But if by greedy strategy we will take the first one, then there is no space for putting the second one. Because the total weight can be only this much. One if you take, you cannot take the rest, right? So greedy can perform any bad as it can. There is no bound, factor bound. Okay. So are you convinced? So are you convinced that it is not obvious that greedy will, okay, there are many examples, greedy will not work. That is why I am now telling you don't, okay, so you cannot just say P of S1. S1 is not guaranteed to perform well. It can go very bad, we have seen, right? So let's now think of this strategy, that it's only a modification of that strategy. You compare which is better, the first k items or the k plus 1 item. Whichever is giving you better profit, take that. That is my solution now. So I am claiming that this will give you at least half of the best possible. It may not give you the best possible, but it will give you at least half of the best possible. So, okay. വെയിറ്റ് വണ്ണേ ഉള്ളൂ, പക്ഷേ അതെടുത്ത് കഴിഞ്ഞാൽ പിന്നെ ബാക്കിയുള്ള സ്ഥലമില്ലല്ലോ ഇടാൻ. അല്ല, ഇത്ര തന്നെ, ഇതിൻ്റെ രണ്ടാമത്തെ വെയിറ്റ് എത്രയുണ്ടോ അത്രയാണ് ബിൻ കപ്പാസിറ്റി. ഒന്ന് കുറയും, അത് മുഴുവൻ ഇടാൻ പറ്റില്ലല്ലോ, പാർട്ട്ലി എടുക്കാനും പറ്റില്ല. ILP. Okay. So if you are allowed fractional items, then greedy is the best. That we already told. But otherwise greedy is very bad. Greedy can go very bad. Okay. Now let's come back to the claim. So if you take the best among these two solutions, it will give you at least half the optimum. So can you show this? Some people have got it, so others please try. I have also written what is the opt LP. So what is opt ILP? How does it compare with this? Less than or equal to this, right? 0 less than or equal to alpha strictly less than 1. So, now what can I say? How will I show that this is the case? Complete the.
ILP is P of S1.
No, that is what I told you, right?
No.
That is what the exercise example told, showed.
Okay.
Integer solution.
After showing that claim, what will be the next?
That is it. So, this means that you can take the best among the two.
That's right.
It is over. So, did you get it? How?
Okay, I choose as two cases. P of S1 will be P1 to Pk. So this will be 1 plus alpha is less equal 1, and this part will be P of k plus 1 will be less than this part.
Okay.
So like equal, greater equal, I am considering this as maximum value is 1. Alpha is less than 1 and N2 less than 1 quantity. So 1 plus I consider this as 1, it will be 2. And
I think it's probably not the correct way.
equality.
No. Why are you comparing it with this one?
That's okay. I consider two cases.
Okay,
Case one
okay,
is
okay.
maximum is P of
Oh,
S1.
okay.
Second one is P of S2.
Oh,
Both
oh,
way.
okay, okay. You are
And that-
taking two cases. Okay.
And alpha value, it is strictly less than 1.
Okay, okay.
So that equality won't be there.
Okay, that will be correct only, but you can do it in a simpler way. What we if I take the sum of P of S1 and P of S2, what do you get? If I take P of S1 plus P of S2, what can you say? 1 to k plus 1, right? Pk, Pi. So this is, so this is greater than or equal to opt LP, right? Because this is only alpha, alpha is less than 1. So actually this is strictly greater than. So, if P of S1 plus P of S2 is strictly greater than opt LP, which is greater than or equal to opt ILP, if sum of two items is bigger than something, at least one of them should be bigger than half. That is the argument. That completes the proof, right. If sum of two values is greater than, say, some b, means something, some at least, if both cannot be less than half, right. So, at least one of them will be greater than half. So, that completes the claim. So, okay. So, that is enough to complete the proof. Now, so the solution is, both are integer solutions, so take the best among the two possibilities. If you choose the first possibility, you will not always win, right. So, we have seen example also, there is a bad factor, can be very bad, right. In that example the factor was this big, right. So, as big as you want you can make it, okay. But this strategy will give you a 2-factor approximation, okay. It is a nice algorithm. Okay. So, now in this session what we will do is, instead of getting a 2 approximation, I told you this problem is approximable to any extent that we want, that is what we are going to see, okay. But before going into that, first we will see to solve this problem exactly. We cannot do it in polynomial time because it is NP complete, but we can have a pseudo polynomial time algorithm, that is like it is a polynomial in n and p. The running time is a polynomial in n and p. If it is a polynomial in n and log p, then it is actual polynomial. This is not like that. This is the running time will be a polynomial in n and p. N and say P max. Okay. It is a dynamic programming based algorithm. So, can you think of some solutions? You can have say dynamic programming, what it does is, from a solution that has been, you will have a table like thing, you have a partially built solution, you will be extending it, right. There will be some substructure optimality, you will be extending it, right, and in the end you will give a solution, okay. So, some people would have studied this also, right. There are multiple dynamic programming algorithms for this problem. There are some algorithms for which the running time is a polynomial in n and w max, and some in which the running time is a polynomial in n and p max. So, we are going to see one in which running time is a polynomial of n and p max. So, let us see what are the different values of profits possible. We told it can start from 0 to minimum profit to in the okay, we let us have that starting assumption as earlier, that any individual item has cost has weight less than or equal to capital B. Weight. So, you can get at least one element, okay. So, let me just to make things simple, let me say the possible profits are in the range. The range is smaller actually, but I can say it is in the range 1 to n into p max. Okay. All the possible profits, the total profit can never go above n into p max, and it is at least 1. Okay. So, the dynamic programming that we are trying to achieve is something that has this many iterations. For every value of I between 1 and n into p max, we will compute the solution iteratively using dynamic programming. If you know something for which the profit is p, how will you know the okay, what are we? I will just write the formulation, maybe that is better. So, this is what we are looking at. What is the best way, I will tell you what it is, best way to achieve profit exactly p some value p, okay, some value p using all the elements, that is our final goal. Okay. What is the best way to achieve profit exactly p? If you know for all different values of p, okay, then you can find out, right, what is the best possible thing. Suppose you know what is the best way to achieve profit exactly p. If some profits are not possible, then we will say it is infeasible. Whatever is possible, the best, the highest one, for which there is a best way, is the one that we will choose.
Something like a rod cutting problem, the partition, like if P is
Something like that, but we can do one by one. We can add one by one.
so P is there, so if I say what is the best way to get K and
So let me also give the other parameter using exactly using as any subset of items A1 to AI. Okay. Suppose you can find this we will form a recurrence and solve it using dynamic programming. So, using only items, any subset of items from 1 to AI, A1 to AI, if it is possible to achieve profit exactly P, then best way means what is the minimum weight with which you can do this, minimum total weight of items with which you can do this. That is what I mean by best way. That is what I will say for each I between 1 and n and P, profit value between 1 and this, okay. Let best set of I comma p represent a set of subset of A1 to AI, I am not allowed to take, for forming this solution, I am not allowed to take elements from AI plus 1 to AN. I am only concentrating on using only the first I elements. If it is possible to achieve exactly profit P in some way, what is the minimum weight way in which I can achieve that? Okay. Profit exactly P can be achieved minimizing the total weight of items chosen. Okay. Let's worry about how to find it later. Suppose I know this. So if this does not exist, we will say it's empty set or undefined. It does not exist. Okay, such a thing may not exist. I will also define another thing. So min weight of I to P is the weight of such a solution. The best way to achieve profit P using any subset of elements A1 to AI, okay, there is a best way. That best weight, the minimum possible weight, right, which is the weight of the total weight of items in this best set, that is my min weight IP. Okay. Weight of items in the set, that set. Okay. If this set is empty, best set IP is empty, then I will say that the minimum weight is infinity. If this set is non-empty and is equal to infinity otherwise, there is no such minimum weight possible. Minimum weight is infinity because it is minimum, it is better to say minimum possible is infinity, so that we know that it is not there. Okay. Suppose we somehow find it using, we will discuss how to, it can be done using a dynamic programming algorithm. After we find that, how do we find an answer for our problem? That is, what is the best possible profit? That is our first question, right, which we started with. Using all the n elements, what is the best possible profit? You can use all elements in the end, right? Okay. So, in terms of this min weight, how can you represent the optimum solution's value? Objective value, objective function value. Suppose you know how to find this for all I and P. Assume. If you know that, then how will you decide the best possible profit of the given instance?
For some weight, the min weight is less than equal to B, then that's the best profit. Else,
for some item, okay, let me try to write down. For some profit P if min weight of P, what is this here? I?
As we use the binary cells that we use, first put P as NP max and I as N.
Don't try to solve now.
Yeah, alright. Like this.
Assume you know how to solve. We will form the recurrence later. If you find it,
The min weight, right?
for every possible I and P.
So I can fix N, that I know.
Okay, so I will combine it with his thing, okay? Because you can, in the end, you are allowed to take any subset of A1 to AN, right? You are not limited, right? In the end, you know everything. It is not excluding anything, any subset, right? So it's better to take every subset of, any possible subset of A1 to AN you can take. For some profit P, if min weight NP is less than or equal to B, there may be many.
We'll choose this and then we'll check it for some higher P, just repeat, then we'll take the maximum P.
Yes, so that is the right answer. So let S is equal to maximum P such that, okay, maximum value of P such that min weight NP NP is less than or equal to B, right? So this is your final answer. If you know this, that is your final this is a min weight max profit value if you want to get the corresponding set, you take that set which was giving this value, right? Fine. This is the profit. The maximum P, see, why did I write this? Because for some profit P, if min weight is less, min weight of NP, N because I can take any subset of A1 to AN, right? Any elements, any set of elements I can choose. That's why it is N. And this is P. If it is less than or equal to B, then only I can take it. If its weight is bigger than P, it's not feasible, right? Our constraint is that the total weight of elements chosen should be less than or equal to B. So that's why he has put this condition that it should be less than or equal to B. But this may be possible for several P's. So the best way is to take the maximum P for which this happens, right? So that's why we wrote, so maximum profit possible is the maximum P for which this is less than or equal to B. And the corresponding, there will be some best set, right? Best set N P for which this happens. So let me call this as, say, S, okay? So S is the maximum profit possible. And so the best set of N comma that S, maximum profit possible, there was some set, right, which gave this value, that is this set, right, best set N comma this particular profit value. There is somebody who exactly got this profit, right, that set is best set of N comma S, right, is the optimum solution. Okay. Fine. Till now is it okay? I did not say how to find it, but I am saying suppose you find these two things, best IP for every INP and min weight IP for every INP. If you find, then we know how to find the solution, the best possible profit and the set which gives that profit. Fine. Everybody following? Now let us see, can we write a recurrence for this these two things, min weight IP and best set IP. If you know it for smaller values, can we write it for bigger values? To start with, you have one item, right? A1 only. You are allowed to take only A1. If you are allowed to take only A1, then what are the possible best set 1P? It's either empty set or the singleton A1, right? You can either take A1 or not take A1. And your min weight IP for different P values you can write, right? So let us try to fill out that dynamic programming table. Okay. Dynamic programming is often associated with a table which you fill systematically. So I is equal to 1, so you are taking only A1. Say profit is equal to 1, profit is equal to exactly equal, okay. You have a matrix. Similarly, you have another matrix for best set, okay. Definition of? S is actually profit. Yes. According to the definition, it's weight. Oh, no. Maximum P such that, maximum profit P such that, what is min weight NP? This is less than or equal to P is satisfied by several profit values, right? This P can vary between 1 and n into P max, right? For some values, this min weight will exceed B, that we cannot take. So you are now, your feasible solutions are those for which the min weight is less than or equal to B, right? You are taking for each profit value, what are the profit values for which min weight NP is less than or equal to B? Okay, all those profit values are achievable, exactly achievable, correct? Not sure? Okay. So let me go back to the this you understood. So what is min weight IP? This is like, so the best set IP will be a way of achieving exactly P profit, P value, profit value P exactly using elements A1 to AI. So best set NP would be our some way of achieving profit exactly P using any of these elements from 1 to n, right, A1 to an. So among these possible ways of achieving profit exactly P, some of them may exceed our bin capacity, knapsack capacity. Such things we are throwing away. That is why I have put a condition that what are the things for which this min weight NP is less than or equal to B. So, I am now restricting to only those P for which I have valid solutions satisfying the constraint.
My concern is only about the notation, because there should be a P inside that bracket, right? Otherwise, if you write outside, maximum amount P is fine. Inside there should be P such that that condition.
Oh, okay, okay. So, I meant this only for every 1 less than or equal to P less than or equal to n into P max. This is what I meant.
Now, before that minimum weight, there should be P column, right? P such that that condition satisfies. We are not considering min weight this one. Maximum of P.
So, this is argmin. Argmin. You have heard of argmin? The argument which minimizes that. Argument which minimizes that. Okay. Argmax.
So it is not separated convertation.
Argmax, argument are similar, typically they are in all the function theories, right?
No, separated convertation that should come inside the bracket. If you are P, it should be P with the column and then the condition.
Okay, I will write again P ranges from 1 to this, okay. In this range, you have a set now. Oh, okay. Okay.
I'm just saying, inside the bracket, P, then the column, then the condition.
Okay, 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 okay. Okay. Maximum P such that min weight n P is less than or equal to P. Okay, thanks. Okay, so everything is okay now? It's okay. Okay, so now let's try to fill up this table of, maybe I'll say min weight. Similarly, there will be a table for best set also. Okay, so can you help me to fill this column corresponding to A1 to start the recurrence? If I know one column, can I find the next column is the next question. To start the base case of recurrence, let's try to write A1P. Let's try to define A1P for every P. Oh, not A1P, this is min weight, right? For every P we need to write. Similarly, best set 1P also I need to write for every P. I am trying to fill this column. So, can you tell me, so any entries, all the entries you can tell me in the first column.
What do you mean by this notation, max?
Maximum value of P for which you can add that P, that is the corrected one.
But it is for, we have to get P profit.
Exactly.
Exactly P profit, right?
So
There is only one profit.
no, the thing is, this we are running for all values of P between 1 and NP max, right?
For all values of profit, we are finding the minimum.
Correct, all possible things.
Among that, maximum profit.
Correct.
But then
So over here you were just just taking the singleton element A1. Yeah. So that will be only for that weight, for that profit to the maximum. You can say it will be.
Only for that profit I can say no.
Yeah, that's what.
Huh?
Yeah, below you.
Okay, so this may be the profit of, this is say our profit of A1, right? For this value,
We have that.
what is the value that I fill here?
W1, the minimum.
W of A1, right? Right? There will be, this is like I am only taking item number 1, not anything else, right? So, only for profit value which is exactly equal to profit of this first item, P of A1, profit of A1. For that value, I know that with weight of A1, I can satisfy that, right? For all other things, this is infinity, right? I cannot satisfy that simply with A1, correct? So, that is how I can fill the first column, right? So, this is W of A1 if P is equal to P of A1, profit of A1, and it is equal to infinity otherwise, right? And what about this set? It is equal to this singleton set A1 if P is equal to profit of A1, otherwise it is empty set, right, or undefined. Let us say empty set otherwise. Right? This is how I start my recurrence.
അതർവൈസ് പറയാൻ പറ്റില്ല കാരണം P1 ആണ് ഞാൻ വാല്യൂ എടുക്കണമെങ്കിൽ A1 വരും, P2 ആണ് എടുക്കണമെങ്കിൽ A2 വരും.
No, not like that. I am allowed to take only for I is equal to 1, I am allowed to take only set A1 or its subsets. I am not allowed to take A2.
ആ സെറ്റിലെ ഓക്കെ അപ്പോൾ I എടുക്കുകയാണെങ്കിൽ I വരെയുള്ള സെറ്റിൻ്റെ സബ്സെറ്റുകൾ മാത്രം നോക്കാം.
Okay, in the first step I am allowed to take only A1 or its subsets, that is like either take A1 or don't take A1. In the second step I can take any subset of A1 and A2, that is either I can take A1 and A2 or I take only A1, only A2 or nothing, right. So, these are the possibilities in the second set to fill up the column. So, how will I fill up the column if I know the previous column? So, let us try to write the recurrence. So, what is min weight? Next column is I plus 1, I plus 1th column, right. Can I write min weight I plus 1 P? Okay. I have to also write best set I plus 1 P. How will you decide that?
The weight of the next added that is being added, it's greater than, I guess, when.
So, there are many cases. If the I plus 1 item's weight is more than, profit is more than P, anyway we cannot take it, right. So, if profit of A I plus 1 is greater than P, not reject, we need to define. This is same as the previous thing itself, right. What was the best way of choosing with I elements, that remains the same. You don't achieve, you cannot anyway include I plus 1. So, don't take it, just take the previous one. Okay. The other option is profit of ai plus 1 is less than or equal to P. Then again you have many ways to do it, right? You have to get exactly profit P using items, any subset of items from A1 to ai plus 1 now. What are the possible ways? Either you try to take the previous one itself, or you take the new one and discard, maybe throw out something else, right? So, how to do that? What is the value? So, you need to compare which is giving you the minimum weight, right? Suppose you are including this item, then weight of ai plus 1 is taken by this item. The remaining space for the other items is weight constraint for the, profit. P of this one is already achieved. P of ai plus 1 is already there. The remaining profit, which is P minus profit of the I plus 1th item, has to be exactly matched by the other elements, right? By a subset of the other elements, right? Right? So, there are two possibilities. One is that you include I plus 1th item, in which case you will have to take profit of ai plus 1. Okay. So, let us try here. Profit of ai plus 1 will come from I plus 1th item. You are taking it, right? These are the two possible. Take it. So, the remaining P minus profit of ai plus 1, you have to recover from elements a1 to ai, right? Okay. And this is one way. So, if this is the case, this is one way of achieving it. If this is the case, what is your, what is the minimum weight? What is the weight, total weight that you are achieving? If this is the option that you are taking, that is you are including ai plus 1 in your solution.
Then min weight of this, P minus this,
So, this is like min weight of using a1 to ai, exactly this value, right? P minus profit of ai plus 1 plus weight of ai plus 1, right?
finding the minimum of this.
Okay. So, this is the weight that you achieve if you were including ai plus 1 in your solution. So, the other way is to not take ai plus 1 in your solution. You have to compare which is the better, right? So, tell me what is it that you will get if you are, what is the other option? You are not taking ai plus 1 in your solution. So, min weight I comma, yes, I comma P itself, right? The entire P you have to match using the first I items itself. I plus 1th item you are not taking, right? So, these are the two possible values. Either you take I plus 1th item, in which case the total weight that you are going to get is from the remaining items exactly get P minus profit of AI plus 1 using the minimum possible weight, and then add weight of I plus 1. Otherwise, if you are not taking I plus 1, then min weight, you have to exactly match I profit P using the initial I items. So, these are the two possibilities. So, whichever is giving you the minimum, take that, right. That is the recurrence. So, in the second case, if the other case, so we have to take minimum of these two. Min weight I comma P and profit of weight of I plus 1 plus min weight I comma P minus profit of AI plus 1, right. So, these are the two possibilities. Either you will get, if P is greater than profit of AI plus 1, you have no option, you have to remain with whatever you had. Otherwise, you have two options, take the best among them, right. Either take AI plus 1 or do not take AI plus 1. Okay. So, the set also you can define, right, best set correspondingly for each of these options. In this condition, if it is this is the condition, then it is the same as best set IP. You are not adding this. Here also, if this is smaller, you will add AI plus 1 to best set AI IP, that is your best set I plus 1 P. Otherwise, your best set I plus 1 P is same as best set IP, right? Correct. So, correspondingly you can define best set also. When you are defining best set I plus 1 P, you can use best set IP. Okay. So, now actually you have the dynamic programming algorithm. We started with this, right. Now, let us fill the next I equal to 1, you have filled the column. So, do you have enough information to fill I equal to 2? If I have filled I equal to 1, you know how to start, base case is solved. Now, do you know how to solve this? What do you want to know to solve min weight 2 comma for every P? Only the previous one, right?
Check the profit of
Check the profit.
if it is greater, then you go for min weight.
Just copy the value from the previous column if it is greater. Otherwise, you look at that difference, right. For that profit you see the previous column and then you add the profit of this item, right. Okay, wait, right. So, using all the values that are available in this column, you can fill up. The recurrence depends only on the previous column, right? So you can fill up this column, then you can fill up this column and so on. So for all possible values of I equal to 1 to n, in this way systematically you can fill up the table, right? So what is the time required to do this? How many iterations are required to do this entire thing? I varies from 1 to n into p, 1 to n. I varies from 1 to n, and initially for this table for every I you have n into p max values. So the total complexity of this algorithm is like n square into p max, right? So that is the solution. You will get the best set also, and we know, if we know the best set and mean weight, how to get the solution, right? We have already seen that. So this dynamic programming algorithm has n into p max, okay. N I varies from 1 to n, p varies from 1 to n p max. So the total running time is this, okay. Other operations are all unit time, correct? Now, okay, so this is a pseudo polynomial time algorithm. Just think for a moment and convince yourself whether you have understood or not. If you have not understood, ask me. Is this algorithm clear?
Best for the minimum, the second case, how we are defining the set.
Which one?
For minimum,
That's,
minimum,
there are two possibilities, right?
yeah, for the second,
If you have chosen, if this is minimum, if this is minimum among the two, then your set remains that as the previous one. Best set I plus 1p is same as best set ip, right? If this is the case, you have to include, take union, insert I plus 1 also to best set ip. Best set not ip, I p minus this thing. These two things I would need.
so for writing, we have to take three cases. If this is the minimum, this is the set. Otherwise, this is the set.
The first case, it's anyway
Yeah,
ip.
yeah, best set.
Okay. It's okay? Now the problem is that this algorithm is a pseudo polynomial time algorithm, right? Anyway, we cannot get polynomial time, this is a pseudo polynomial time. But what are we interested in? We are trying to find approximation algorithms, right? With factor which is better than 2. Okay. So the idea is to actually convert this dynamic programming algorithm to a polynomial time algorithm. Okay, but we cannot exactly do it, right? We cannot get polynomial time. So if we are trying to achieve polynomial time, we have to suffer some errors, right? So we are ready to sacrifice some precision to get polynomial time running time, okay. So now why was this taking that P max. Why is P max coming into the running time? That is because the maximum profit was the number of iterations which we had to do, right? Right. Correct. So, if we somehow produce another instance of the problem where the profit is not that high, profit is small. If the maximum profit is small, this runs in polynomial time, right? If the maximum profit is only n, say, then this is an n cube algorithm, right? The maximum profit, that magnitude of the profit was only n. Then this algorithm itself runs in polynomial time, right? So, the problem is that some profits have larger magnitude, right? So, let us somehow solve that issue. How can you create another instance of knapsack problem in which the profit values are smaller?
You might take the logarithmic of the polynomial of the profits.
Logarithmic
Polynomials, because the relation will still hold.
logarithmic one problem is that some values it cuts down drastically. Say 10,000, if you take log, it comes down very drastically, right? And if you have profit 2, it comes to 1. So, the reduction in 2 is by 1 and the reduction in 10,000 is by 10,000. If you take log to the base 2, right, you will get something like very small value, right? So, the thing is, the reduction from 10,000 to this small value is very large, whereas 2 to 1 you are taking log and the reduction is only 1. So, the answer may change. If you find answer for the new problem, from that you may not be able to get a good approximation for the original. So, the idea is this now. So, you have an instance I given of knapsack problem. You want to convert that into another instance I dash in which weights are in which the profits are small. This is one side, but this is not sufficient. So, then what will we do? We will solve this, right? This we know how to exactly solve because profits are small. If profits are small, we know how to solve in polynomial time, right? If say profit is only n, maximum profit is only n, we know how to solve, right? Something like that is what we are trying. But the problem is, suppose you solve it, then you need to somehow get an approximate solution for I, right? So, he told take logarithm of all the values, all the profit values, original profit values. But the problem is, suppose you get that, then you try to get the solution for this, the factor by which the profit may change, the optimality, that bound we may not get. Any other way without, is there a uniform way in which the effect of this change of reducing the cost is similar for different values of profits?
Divided by kind of things.
Yeah, so you just divide it and scale it down. That is more natural also, right? Don't take log. Log is like a non-linear effect it is creating, right? So, let us try to divide it by some number, big number, which depends on the maximum profit, right? All the profits, if you divide by some number which depends on the maximum profit, it will come down. And then we need integer valued weights, if you remember. All the weights should be integer valued. All the profits should be integer valued. weights we are not changing. Okay. So, if something is happening, we should take either a seal or a floor, something like that. If you, when you scale it down, if something becomes fractional, you take the seal of it. Okay. So, that is exactly what is the strategy. So, let me define, this is only to scale down. The values, the profit values by dividing with some term that involves P max. Okay. So, let me define that term with which I am going to divide all values. Okay. So, okay, I have also, so my aim is to get a 1 minus epsilon factor approximation for knapsack for any epsilon. Oh, you are telling me my epsilon is 0.1, then I am supposed to give you a 0.9 factor approximation for knapsack, which runs in polynomial time. If you tell me my epsilon is 0.01, I am supposed to give you a 0.99 factor approximation algorithm for knapsack, which runs in polynomial time. But this polynomial, then what is the sacrifice that I am making? Is the polynomial, the time the same in both the cases? Can it be? It cannot be, right? So, the running time will change as a factor of epsilon. Okay. So, because epsilon we are thinking as small quantities, right, less than 1. So, we will say it is a function of 1 by epsilon. If your epsilon is 0.1, my 1 by epsilon is like 10, right. Okay. So, my running time will be changing as a function of this 10, if, okay, function of 1 by epsilon. So, if you want more precision, you will have to spend more time. The time is a polynomial once you assume epsilon to be a constant. For any constant value of epsilon, this is true. Actually, it need not be constant also, it can be even functions of n. Okay. For any fixed epsilon, okay. So, suppose along with your instance, you are also telling me this is my epsilon. Give me a 1 minus epsilon factor approximation algorithm for knapsack. Epsilon cannot be 0, I cannot exactly solve it. So, you have to give me an epsilon which is greater than 0 and which is less than 1. Okay. Like 0.1, 0.01, anything, as close to 1 as you want. Then for each value of such epsilon, I have to give you one algorithm. So, the running time will depend on epsilon also, 1 by epsilon also. So, my number of steps, my scaling factor is going to be dependent on epsilon as well, not just P max. You are giving me epsilon, any epsilon you give, I have a way of scaling down. So, the scaling factor k will be, you can have different options, but one possible option is epsilon into P max divided by n. If we divide all profits by this k and take the floor, what is the maximum profit? P max becomes n by epsilon, right. So, this is the algorithm. So, this is 1 minus epsilon factor approximation for knapsack. Okay. So, algorithm is this. Let us define a new profit function, profit dash. Original profit function is profit. Okay. So, I am just scaling down. Profit dash of AI is defined as profit of AI divided by this k floor. I am just scaling down. Scaling factor is k, where k is this thing, epsilon into P max by n. Okay. This, if you what do you say, play around with sometime, you will also find a similar thing. This is not a magic. Okay. K is not a magic, it should depend on K, P max, so that the dependence on the original profit value on P max is removed, and it should depend on n, n maybe, but epsilon 1 by epsilon it should depend on. So, that is why these things are coming out. Okay. If this is the case, okay, then you get a new instance, right? New instance. So, what is the new instance? Items are the same, weights are the same, but profit is scaled down. Profit is using the new profit function. You have a new knapsack instance.
It may happen that for some the profit gets increased, right? If the epsilon is too small. Because
See, all the values are smaller. Now we have to, I haven't told you how to get the original, right? So, you basically you will be taking the same set which gives you the optimum in the reduced the I dash. That is the algorithm.
no, basically we cannot say that profit dash of AI is less than or equal to profit of AI. That we cannot decide.
It is, right, because you are dividing it and taking as floor.
No. For example, for P max, initially for some item was P max. So after modification it becomes n by epsilon.
Yes, n by epsilon.
What if n by epsilon is greater than P max? It can be, right, because epsilon I can take as small as possible.
What are you saying? N by epsilon is?
N by epsilon can be greater than P max, right? If I take epsilon sufficiently small.
Like what? See, if the maximum profit is very small, right, you do not even need this approach. P max is very small. Say,
No, I am not saying P max is small. I am saying epsilon is small.
I understand, but what I am saying is, even if you have something like epsilon is a function of n, say epsilon is like 1 by n cube, anything, right? Even in that case, you are okay with your original algorithm. You do not need this. See, epsilon, say it is 1 by n cube, take one typical value. If epsilon is a polynomial function of 1 by n, okay, or what do you say, 1 by epsilon is a function of a polynomial function of n. Even in that case, your original algorithm, right, it will run in polynomial time, because your P max will be a function of a polynomial function of n. then your running time is n square into p max, right? Total thing will be polynomial. But actually we don't have to take profit dash of AI. I don't actually need that relation. I'm not going to use that relation. Okay. Algorithm is not complete, right? Okay. So this is the scale down values. Scaled values, say, I'm not saying scale down, but the intention is anyway scaling down. If it is increasing, then I don't need this basically, right? That means the profits are small. Okay, I am scaling down because I want to bring P max down. I mean the maximum profit max dash should be small. Okay. Okay, whatever. I am aiming a running time which is a polynomial in n and 1 by epsilon only. Okay. So the next step is, so we get a new instance. We get a new instance of knapsack problem. With same weights as original. Profit function is the new one. Profit dash is the function. So you run the algorithm, your pseudo polynomial time algorithm, you run on this reduced instance. What is the running time? Run pseudo polynomial time algorithm, dynamic programming algorithm on the new instance. Okay. Let S be this let C be the set of the best set. Okay, that you found in the end. So the same thing you will say that is also a approximate solution for the original instance. You solved the problem for the reduced instance, so that you can solve optimally, right? It's a pseudo polynomial time algorithm, but you can solve it exactly. Solve it and return whatever you get as a solution, that itself you return as a solution for the original problem. This is our algorithm. Okay. So now we have to say certain things. First, that this solution is feasible, right? It is not violating any constraint that you need to argue. Then you have to say its cost is not very high compared to the best possible for the original, right? And its running time is polynomial time. These three things we need to show. So there are three things. One is claims. One is that C is a feasible solution for the original problem. Second claim is that this algorithm runs in time polynomial in n and 1 by epsilon. Okay. Third claim is if you take the original profit function, profit of C is greater than or equal to 1 minus epsilon times opt of I. These three claims I need to prove, okay, isn't it? That is sufficient, no? I need to show that this solution is feasible for the original problem. I need to show that running time is not high, polynomial in n and 1 by epsilon. 1 by epsilon I need to use because for getting some battery down. Okay, so I need to show that the running time is a polynomial in n and 1 by epsilon, and also that if I give this as a solution, then the profit with respect to the original profit function, right, it is within 1 minus epsilon factor, it is very close to 1 minus epsilon factor, close to the best possible as per the original profit function. So, can you give me a proof why C is a feasible solution for the original problem? Why is this a feasible solution for the original problem as well? What is the feasibility condition? What is the constraint? Weight, right? Sum of the weights of chosen items should be less than or equal to capital B. B also I did not change, okay, in this transformation. So, automatically any solution that you find for the first one, second one will be a solution for the first one and vice versa, right? If you find a solution for the first one, it will be a solution for this. If you find a solution for this, it will be a solution for the other also. Valid solution, feasible solution. Only thing is optimum values may change during this transformation. Okay?
Okay, we will take it as np max by epsilon, right? The k.
Oh, 1 second. Let's see how this, let's see, okay, maybe. So, my running time has to be a polynomial in n and 1 by epsilon. Am I getting it or not? What's my running time? N square into P max, right? P max becomes P max dash is P max divided by K floor, right, which is right. This is my maximum profit as per the new profit function, right, n by epsilon floor, right. So, what is my running time? That is okay, right, isn't it?
You are trying to reduce the profits very down.
And do not worry about that. See, this is, now this has no depends on P max anyway, right? Okay, running time? Running time? Let me write it this way. So, this is very easy, right? Because weights do not change and our capacity doesn't change, this is the same. So, this one running time is n square into P dash max, which is order of n square into P dash max is this is order of n cube by epsilon, right? This is okay. This is our running time. I am ready to allow running time which is any polynomial of n and 1 by epsilon. Okay. Okay, so this is also true. This is running time is polynomial in n and 1 by epsilon. Okay.
What if epsilon is like very small?
Then running time is more, but what can I do? See, you are telling me you need a approximation. Anyway, it cannot be exactly 1, right? I mean, epsilon cannot be 0. If epsilon is 0, it's an exact algorithm. I know it's going to be not possible in polynomial time. As you go closer and closer to epsilon 0, your running time is boosting up.
So see, basically in the profit prime AI,
Huh.
we are scaling it up if we take A as this thing, because epsilon is between 0 and 1.
Correct, correct. That is true. But originally it was n square into p max. But this is not p max or anything, right?
I'm just saying if we take the other way around, it will be order n epsilon, right?
Which one?
His question is, instead of taking epsilon p max by n,
Huh?
take it as n p max by epsilon.
And then order will be n epsilon. And epsilon is between
I didn't get.
A, we can take it as n p max by epsilon.
This way. Huh? Huh. See, epsilon is a very big value. I mean, epsilon is
Between 0 and 1. So it will be order.
so.
Huh?
Epsilon is.
Yes. Yeah, it will be 0 for
Okay. Okay. I am see, for any of these problems for which we are trying such approximation algorithms, right? It's always a function of 1 by epsilon. It's going to be a polynomial of 1 by epsilon. As I see, the thing is, as I reduce epsilon, running time is going to increase, right? So that intuition is enough, isn't it? As I want more accuracy, running time is going to increase. So it is not like this way dependent, the same way, it's inversely dependent. Fine? Okay, so what about this? We need to show this. So what's the relation between profit dash and profit? So profit, with respect to profit dash, C was the optimum. And with respect to P also, C was not very bad. That is what we are claiming. Original profits also, C was not very bad. So let's prove it. Okay. So I need to say that profit of C is not too small, right? What is profit of C? Sum of profits of all the items in C, right? That is how it is defined. So for any item, I have this relation. How did I define? Profit dash of AI for any I is equal to profit of AI divided by K floor, right? So I can say this is less than or equal to this, right? And it is less than or equal to, this is floor, so I can write correct? It lies, if I take the floor of this value, it is equal to this, that means this plus 1 is greater than, right, profit of AI plus 1, profit dash of AI, not profit of AI, profit dash of AI plus 1, correct? So, or in other words, I can write profit of AI is greater than or equal to k times profit dash of AI, right? So, what about profit of C? Profit of C is the sum of profits of all the items, right? So, this is greater than or equal to k times sum of I in C. Okay, I am abusing the notation, but you understand, right? Profit dash of AI, which are in C. AI in, I can say AI in C. Okay, now there is no abuse, right? Into, yeah, K I have taken out. Fine. Profit of C is greater than or equal to K times sum of profits of profit dash of all those items in C, right? Now, with respect to profit dash, C is the optimum, right? Suppose we have an optimum, say O, for the original problem. Let O be an optimum solution for the original problem. Original instance. So, O is a feasible solution for the new instance, so the new problem also, right? I told earlier, even if you change the weights up or down, the feasibility does not change, right? So, see, O is a valid solution for the new instance also, right? Valid solution, may not be optimum. So, what can I say? Say this C we have found right, this is the best for the new instance, and O is some solution for the new instance. So, how does their values compare? With respect to profit dash, for the new instance, C is the best, O is some solution. So, profit dash of C is higher, right? It is not lesser. So, I can write, so this thing I can write if I sum up. So, this is your opt dash. So, this is your opt dash for the reduced instance, the optimum opt dash, right? And this is some solution, right? This is true. Is it true? if you are taking O instead of C for the reduced problem, for the new profit function, C is better, right? That is what I have written. C is not worse compared to O. Now I will use the other side of the thing. So, profit dash of AI, what can I write? Profit dash of AI is greater than or equal to, or I will write K times profit dash of AI plus K, right, is greater than profit of AI, right. If I sum it up, then K into profit dash of AI now I am taking O, okay, plus what is the term? K times cardinality of O, right, number of elements. This is greater than sum of AI in O profit of AI, right. So, sum of AI in O profit of AI, and this thing I have, right. So, I can substitute. So, that means I can write it this way, right, this term becomes minus there, right. Right, just rearranged. Here, no, I am just saying that for any element this is the case, I am just summing for all elements of O. This is for each element that is the case. So, I am just summing over all elements of O. So, I get that, right. Because there are O elements, I got that second term cardinality of O, that many times K gets there. So, this is a minus, right. So, I will write here K into profit dash of sum of profit dash of AI, that is the term I have here. I can write it as actually summation of AI in O profit of AI minus K times cardinality of O, right. What is this? What is the sum of profits of all items in O? Is opt, right, that is opt, original instance, profit function, not profit dash. So, this is equal to opt, let me write opt itself, right, opt minus now K is we define K as epsilon into P max, right, P max by N, right, okay. So, this is greater than or equal to opt minus kn, right, because this is sum O and n is the total number of elements. Okay, this is also true, right. This is a quantity, I am reducing a larger quantity, so this is true. So kn is equal to epsilon p max, right. This is only some numerical manipulation now, okay. Kn is epsilon p max. Can I write here? Can you see it? Can everyone see it if I write here? This is equal to opt minus epsilon p max. I should get opt minus epsilon opt. So, do you see why? I should get opt into 1 minus epsilon, right. I am saying that profit of C is greater than profit of C. Then the reduced instance solution with respect to the original profit function is at least opt into 1 minus epsilon. That is what I should say. So, the step missing is that I should say that this P max is less than opt, right, less than or equal to opt. Is that known to you? Is that known to you? P max is less than or equal to opt? Why? It is the profit of a single item. We initially assume that any item which is not feasible at all, its weight is more, we are discarding. So, with that assumption, any single item's profit will be less than or equal to opt. Any single item is feasible, right. So, it is a feasible solution, optimum solution is better than that. That is all. So, that is the assumption that I initially made. Any item which is not, single item that is not feasible, I am removing from my instance initially without loss of generality. So, this is true because each profit of AI is less than or equal to weight of AI is less than or equal to B for all I. Therefore, profit of AI is less than or equal to opt. Okay. So, I get opt is greater than or equal to P max. So, I get this. So, this is opt into 1 minus epsilon. Okay. So, what did we do? Should we know the optimum solution to find the algorithm? No. Okay. I use the optimum solution's existence to prove the approximation guarantee. I do not need to know what is my algorithm. Algorithm is here. Here I am nowhere taking into consideration what O is. I do not know what O is. If I knew O, my problem is solved, right. I do not know O. I am just scaling down the weights, scaling down the profits to get another instance. I know that if the weights are small, I can solve it in polynomial time, in real polynomial time, using the actual pseudo polynomial time algorithm, dynamic programming algorithm. So, I solve it for the new instance. Whatever I get, is a valid solution for the original instance also. So, I will say okay, I will just return this as a solution for the original instance. That is my algorithm. I do not need to know O for this doing this. But where did I use O? For analysis. When I wanted to show that C is 1 minus epsilon good, that time I used the property that there is some optimum solution and my solution is not very bad compared to the optimum. So, okay. If you recall, in almost all the problems, say when we did yesterday's 1.5 factor approximation or 2 factor, everything, when we wanted some lower bound, we were depending on the existence of the original optimum solution. So, that is how we got a guarantee on the upper what we are getting, but the solution itself does not need to know anything about the optimum. We have some related thing which is polynomial time solvable. This is also the same thing if you look at it in some other way. The reduced instance is a related problem which is polynomial time solvable. So, you used it to solve that original problem. Okay. So, any questions regarding this?
Profit in C will be greater or equal to profit in the original, sum of new profits with respect to how?
Because C, what is C? C is the, according to the profit dash function, that is the best. That is why O is according, yes, but according to the new profit function, C is the best. So, the total cost of C is better than, according to profit dash, C is better. That is why. Right. So, for this problem, for any given epsilon, you can find a 1 minus epsilon factor approximation with a running time which is polynomial in n and 1 by epsilon. Okay. Such algorithms are known as FPTAS algorithms. Okay. Fully polynomial time approximation scheme. So, it is a scheme. For every epsilon, you have a different algorithm actually, in some sense. You are cutting down, the scaling factor differs for every epsilon, right? You are given a new epsilon, you will have different values, right, reduced instance. So, this type of algorithms, so it is not one algorithm, it is an algorithm scheme for every epsilon. So, this is known as a fully polynomial time approximation scheme. Okay, FPTAS. So, the running time should be for every epsilon running time is a polynomial in both n and 1 by epsilon. Okay. So, my lectures are almost over. I just want to ask you one thing. Now, you have seen several algorithms for minimum vertex cover, right? Approximation algorithms. So, can you tell me why minimum vertex cover cannot have an FPTAS? Minimum vertex cover problem, we cannot approximate this close. Even if we have running time, it is a function of 1 by epsilon and all, it is not possible. Why? Minimum vertex cover problem has no FPTAS. Why? with whatever you know you can find it, and it's a simple thing. So you should derive a contradiction. If there is an FPTAS for MVC problem, P equal to NV, that kind of a conclusion you should derive. In some sense, this problem we are able to get this FPTAS because we are playing around with these weights and all, which are usually not a function of n, which are very big. Okay. MVC and all, we do not have that kind of a I am asking for not minimum cost, minimum cardinality vertex cover, okay, not minimum cost. So, minimum cost is a special case of it's a generalization of minimum cardinality, right. So, minimum cardinality vertex cover problem. Even that cannot be solved, then the minimum cost also cannot be solved. Right. So, even this is true. Why? If you can get an FPTAS for minimum cardinality vertex cover problem, what will be the contradiction? P equal to NP kind of a conclusion you should be able to derive, unless, okay, unless P is equal to NP, okay, that always, okay, goes unsaid.
By taking sufficiently small epsilon, we can determine the actual cardinality.
Correct.
Check for all the subsets of with that much elements from n.
I am trying to find only cardinality.
No, solving the problem, right? I am saying we can solve the problem in polynomial time by checking n choose k. If suppose k is the cardinality, if I get by using this algorithm.
Okay. Come again.
If suppose by using this algorithm, I get the cardinality as k. Because by taking epsilon small,
this will also give me a solution, not only cardinality, it will give me a vertex cover also.
Okay. That is a polynomial time.
Which is a real optimum vertex cover, right? That is what
optimum, you. Because by taking less than anything less than 0.5,
epsilon less than 0.5 will not guarantee. 1 plus epsilon into n. 1 plus epsilon into opt is what you will get. But you can take epsilon very small, okay. This is saying for every epsilon such a thing is there, right. Take epsilon 1 by n or smaller than 1 by n. You can take even smaller than that, right. Okay. Take any epsilon which is smaller than 1 by n. N is the number of vertices in the original graph. N minus? What is k? Okay. Suppose minimum vertex cover of G, given graph G, okay, has cardinality k, small k. Okay. So what will your FPTAS find? One solution which is of size. So FPTAS, if it exists, will find a minimum vertex cover of G of size less than or equal to, this is a minimization problem. So it will be 1 plus epsilon. 1 plus epsilon times k, right, k is opt. So I have taken epsilon less than 1 by n. So this is less than okay. What is this? This is a strict less than, okay. What is this? So I am saying the FPTAS will give me a minimum vertex cover. It will give me a vertex cover, not that I don't want to write vertex, minimum vertex cover, a vertex cover of size less than k plus k by n, but this is actually less than or equal to k plus 1, right. If you see the whole sequence, this means that this vertex cover, say if it is S, then cardinality of S is less than k plus 1, that is what I derived, right. Then what is it? It should be equal to k, right. It is an integral quantity, a vertex covers cardinality. So if it is of size less than k plus 1, it cannot be anyway better than k plus 1, k, because k is the optimum possible. So it means that S is of cardinality k itself, right. So implies S is of cardinality k, because MVC was size k, it cannot go beyond below that. Okay. So if you have an FPTAS for MVC, you can exactly solve MVC in polynomial time in n and 1 by epsilon. 1 by epsilon is also like 1 by n only, right, I mean n only. So it is together, it is polynomial time also, a polynomial time algorithm for MVC will be obtained. So for such problems we cannot get. For knapsack we could get. So that means there exists some epsilon such that below that factor 1 plus epsilon you have no approximation algorithm for MVC. This shows that if you want to really show that epsilon is say 0.25 and all, you need more machinery. This is easy. There exists some epsilon below which it is not possible. That is easy. But that epsilon can be very close to 1. We don't mean, right. But if it's, you want to say that it's a constant factor which is like 0.25, you need more stronger machinery. Such machineries exist, and most of it is using some famous theorem called PCP theorem. PCP is a different type of verifier. Like your NP verifier, there is another type of verifier called probabilistically checkable proof, that is PCP. So there is another theorem which gives a different characterization for this NP class, and using that characterization we get stronger inapproximability results. Just like you got NP hardness results using NP type of that kind of verifiers, if you have some different type of verifiers, you can prove inapproximabilities also. Okay. So the book which I followed is, you have probably got a copy, no? Approximation Algorithms by Vasirani, Vijay Vasirani. So there are, it's a very good book. There are many more things available in the book. If you are interested, then you go and read it. Okay.